working in optical transport network. So in these networks, nowadays they are facing a problem of traffic growth. So every year, 30% of traffic growth rate is increasing. So this is due to the new services like cloud computing, high-speed mobile networks, and also the nature of the data, like video and streaming. For this reason, the first solution that the network providers will adopt is to introduce a new advanced modulation scheme with a high efficiency, higher efficiency in spectrum. Another new technique that will be used, and I want to stress, is the introduction of flexible WDM grid. And nowadays, it is used a fixed grid. That it means that every new connection is, for every connection is allocating a fixed amount of spectrum, even if the demand requires less bandwidth, so even if it's not totally used. With the introduction of the new flexible grid, we can avoid this issue, so we can exploit better the spectrum, and we can exactly allocate the spectrum needed for the connection. So despite this new technique, we have also some new challenges to face. The first one is the fragmentation problem, and the second one is the recovery when a failure occurs. So in the first problem, let's assume you have a bandwidth like this, occupied like this. Since the connection are dynamically established and released, assume that 3 connections are released in this case. Now, if a new connection that requires a lot of bandwidth comes, it's possible that it cannot find a space to be allocated, even if the total amount of bandwidth is enough. So in this case, we have blocking of the connection due to the fragmentation. The second problem rises when we have a failure. In this case, we have many connections that fail, and we need to recover all of them. So in this case, since we have many connections with high speed, so with high bandwidth requirement, it's possible that we can find, with difficulties, we can find available spectrum to allocate all of them. Moreover, the previous problem, so the fragmentation, makes the situation even worse to find a possible bandwidth. So, what we have proposed in this thesis? The proposed solution to face this problem is called sliceability, and it's a functionality that consists on serving the capacity demand rather than with a single connection by using multiple connections. This can give some advantages, in particular 3 advantages. The first one is that it's easier to allocate a sub-connection because it occupies less bandwidth. The second one is that we can exploit multiple paths. So rather than using a single path, different sub-connection can take different paths. The third one is that we can also consider, in case of failure, a partial recovery. So if we have failure, we can partially recover the bandwidth, rather than totally block. So in this picture, it shows that from the right, we have a connection of 400 gigabits that can be split in 200 gigabit connection or 100 gigabit connection. I want you to notice that when we further split the connection, also we are increasing the bandwidth occupied. So we cannot just simply trivially split the connection as much as we can, because we are wasting the bandwidth in this case. So what I have proposed is an algorithm called adaptive split that can use the sliceability in a better way. So how it works? The goal is to minimize the blocking probability of the connection, of course, while keeping by using as less spectrum as possible. How it works? First of all, it tries to allocate the connection as a whole, so the total capacity in a single connection. Only when it is not possible, it starts recursively to split the connection into multiple, so the capacity into multiple connections in equal parts. So now I've presented the idea. Now let's see how it's concrete. It has been concretized in the thesis work. So the thesis work is formed by 2 main. It's divided in two main tasks. The first one is the implementation of a simulator for flexible optical transport network. The second task is to evaluate the sliceability using the simulator implemented. So regarding the implementation, I have to say this, in particular regarding the optical transport network. These optical transport networks are subdivided in two planes, two functional planes. The first plane is the data plane. It's where the data are switched, optically switched. The second plane is called control plane. That is the most important because it performs tasks like the routing and the provisioning of connections. So this is the plane, the control plane is the one that has been implemented. So the control plane in particular is it's based on the GMPLS protocol suite. This GMPLS protocol suite is composed of two main protocols that I have implemented from scratch. One is the open shortest path first protocol. The second one is the reservation protocol. Both has been also extended for working with the flexible grid. So the implementation has been done with the C language programming and a tool, a framework, an event-driven network framework has been used. It's called OpenNet Modeler. So briefly regarding the implementation, so that we can go later for the simulation part. In the OSPF-T protocol, the main tasks are the main functionality are the link state advertisement and the spectrum availability advertisement. Exchanging these two information, it is possible that when a new connection arises, it's possible to find a suitable path that has enough spectrum to accommodate it. So this problem of finding a suitable path is called routing and spectrum assignment. So after the routing spectrum assignment is solved, we need another protocol, that is the reservation protocol. And this protocol is the one that exactly starts to exactly allocate the capacity, the spectrum over the links. So all the links on the paths must reserve the spectrum that for the connection. So this is the protocol that is in charge of doing it. So it can release an established connection, of course. So now the simulation part. In the simulation part, I have considered two different architectures. So the first is the distributed architecture. Second is decentralized. For each of these architectures, in particular, we studied two cases. One case when new connection needs to be established, and this is the provisioning case. Another one when a connection needs to be re-established. So when a failure occurs and the connection needs to establish again, it's the recovery case. For each of these study cases, three algorithms has been compared. So the first is when the sliceability, of course, is not used. We call it no split. The second is when, the other two is when the sliceability is used. In particular, in one of the two, the sliceability is used by splitting the demand, the capacity demand, into as many connections as possible. The last one is when the adaptive split algorithm is used. So it's the most interesting for us. So the topology that I have considered is a European network. It's based on 27 volts. And we have around 3 terahertz of spectrum for each link. So now let's start with the distributed architecture. In the distributed architecture, the routing and spectrum assignment problem is solved separately by each node. So when a new connection comes, each node solves by itself the routing and spectrum assignment. So it starts to find a path, a possible path. So in particular, in the provisioning, so when a new connection needs to be established, we can see that we have obtained this graph for the blocking probability. So this is the graph for the connection, how many connections are blocked over the total connection generated. So in particular, this graph is as a function, it shows the three different algorithms as a function of the network load. So we can see that in the case of max split, we have the worst blocking. So it is the curve with the square. Then it is followed by the no split algorithm that perform not so good. The best one is the adaptive that can achieve a lower with respect to the other, a lower blocking probability. In any case, we can see that between the no split and the adaptive split, we don't have a huge gap. So why this? In order to understand this trend, we need to subdivide these graphs, these curves, into different components of blocking. in particular 3 components of blocking that are forming the overall blocking that I just showed. So we have, first of all, a routing blocking, that is the red curve. The routing blocking is the most important for us because it's the one where the sliceability can act and it can decrease. So the routing blocking, what is the routing blocking? The routing blocking occurs when the routing and spectrum assignment problem fails because there is not enough spectrum, so no any path can be found with enough spectrum to accommodate the capacity, the connection. So in this case, so now this is the routing blocking. And of course, when we can also the capacity, the amount of spectrum that we have available, it can be, we can block also because not because we don't have spectrum, but because we have fragmentation, as I introduced at the beginning of the introduction. So the other 2 blocking components are the forward blocking in green and the backward blocking in blue. The forward blocking occurs due to a mismatch between the information that a node has when it computes the routing spectrum assignment and the real state of the network. So it's possible that the information is not up to date, so the routing spectrum assignment is solved. But then when the reservation starts, effectively there is not enough spectrum on the path chosen. Okay, so we have forward blocking to this reason. In any case, it's quite low, this component. Something more relevant is the backward blocking, the blue one. In this case, we have blocking because many connections, more than one connection, that has at least one link in common in the path, are choosing the same spectrum. So in this case, only one of the connections can reserve the spectrum, all the other are blocked. So for this reason, we see that this component is very high. So due to this reason, the overall blocking doesn't have enough gain. We don't have enough gain between the adaptive split, our algorithm, and the no split. Okay. So let's see what happened in case of recovery. In case of recovery, so this is again the graph about the blocking probability, but in this case only those connections that needs to be reestablished, so recovered. So I want you to notice, in particular on this slide, the backward blocking. So the backward blocking is very high, so it overwhelms all the other curves. So in this case, we have so high backward blocking because many connections are trying contemporarily to be established. So it's high probability. Many of them are choosing the same spectrum, the same slot of spectrum. So due to this case, we have this high component of blocking. So even if the routing blocking for the adaptive split is very low, in this case we have gain, but it's not so evident. It's more clear in this graph. In this graph shows the percentage of total capacity recovered after the recovery procedure. So we can see that the adaptive split can recover more than the other, especially for higher network loads. But in any case, also for lower network loads, we can see that we cannot reach the 100% of recovered capacity. This is due to the backward blocking, not because we don't have enough spectrum available, but just because many connections are choosing the same spectrum. So for this reason, we also studied the centralized architecture. In the centralized architecture, we can avoid the backward blocking and the forward blocking, because in this case, the routing spectrum assignment is not solved by each node, but is solved by a centralized element called path computation element. In this case, the path computation element can keep track of all the connections, all the ongoing connections, and it can avoid to choose twice the same spectrum, spectrum slot. Okay, so in this case, it's impossible to have backward blocking. In fact, as we expect, this is the correspective graph in the case of distributing. We are in this case in a centralized, again in the provisioning phase, so when a new connection needs to be established. You can see that the backward blocking and the forward blocking are null, while instead we have just the routing blocking. In this case, we can appreciate the gap between the adaptive split and the no split. In fact, we have one order, even more, one order of magnitude difference between the two. So it means that 10 times less connections are blocked. So let's see what happened in the recovery. In case of recovery, the result is even better, because for each network load, we can see that the adaptive split has a lower blocking. So for each load, we have lower blocking, so we can recover more capacity. This can be even seen better in the capacity recovery, the total capacity recovered. In fact, now we can see that for the adaptive split, we are always above 90% of the capacity recovered. While instead, for the no split case, we are always we are below 80% for high load, for example. While instead we were above 90% for the adaptive split. And another thing that I want to stress is that for low network loads, we can recover the entire capacity, so 100% of capacity. So in conclusion, we have seen from the simulation that this solution, this functionality is effective. So we think that it can bring some benefit for the optical transport network. So thank you for your attention. If you have any questions.
Could you comment on which are the main implementation problems in real applications?
Yes. So in my case, I have implemented these two protocols. That is a quite tough problem, especially when you need to follow some standardization. So like the RFC, because there are many standardizations, so many RFCs that you need to follow. And in this case, I have implemented two protocols. So the main effort was on the RSVP protocol. In this case, you need also to consider, for example, here I have implemented a state machine. In this case, you have to consider that when you have many connections, for example, you need to keep track of all of them. So you need to fork so you need to keep many child processes that needs to take into account all the ongoing connections. So you need not only just one state machine diagram, you need many state machine diagram to cope with this problem. So I don't know if I answered your question.
But I would ask again, I mean, you said that there are a lot of benefits, that's fine, but what would be the drawbacks of doing this split stuff?
Okay, the drawbacks, of course, is that we are occupying more capacity, of course. Okay. So we are occupying more spectrum. If we can use it in a smart way, we can have a gain. Mm-hmm. But if we are not using it in a smart way, we can also see that in the case of smart split, we have less capacity that is recovered because we are wasting our bandwidth. Mm-hmm. So one possible drawback maybe could be more related to the hardware part rather than the software part. Because maybe when you split the connection, then you need also to the multiplex of them. So you need also to consider that if you have traffic that is flowing in one path, so flowing some link, maybe the other taking a longer link, so then you need to reconstruct the information at the end. So this could be an issue. More hardware issue probably than software.